We've been talking about Laplace u equal to 0 in polar coordinates. So I should mention I'm slightly behind, but it's okay. So we've got a test coming up next week. The test covers just up through this Laplace u equal to 0 on polar coordinates. So the next topic, which we'll talk about, is the Fourier transform. And so that won't be on the test next week. Okay, so we've covered everything we need thus far for the test and the homework that's due this Friday. Also, please note that all of the project information has been made available on Canvas. The folder was released on Friday, and you can, if you go to Canvas, you can see under the project tab all the information about the project. Yeah, so we've been talking about Laplace u equal to 0 in polar coordinates, and the kind of foundational problem that we start with is where the domain here is this disk, this circular disk. And, you know, the domains are very important. In PDEs, you know, what we start to see is that it's all about what's the domain, what's the boundary information, you know, on the domain, and how that affects the solution at the end, certainly for Fourier series in terms of determining the coefficients. So here, because of the polar form, which, you know, I won't go over, we have this r in the denominator as well as an r in the numerator. And so that creates some certain mathematical issues. As you know, we don't like to divide by 0. So here in this circular disk domain, 0 is included. And so we need to, you know, make some caveats to handle that. And so what we do is we make the assumption that our solution has to be bounded at 0. Then how does this solve things? Well, when we're doing our separation of variables, this assumption will, you know, force us to throw away certain solutions that come from separation of variables. And it's at this point that I want you to be very aware of that this, you know, this is entirely because of the domain, of the geometry of the domain. You know, if we were, for example, in an annulus, an annular region that did not include the center, then we would not need this restriction. And I'll come back to that point in a second. The other condition we have, it's not really periodicity. It's really, I mean, it turns out to be periodicity, but the reason is really just from the geometry that if we fix a point and fix a radius and go all the way, you know, go around one revolution, you're right back at the same point. So we have that as a fact of the geometry, and then we further assume that the derivative with respect to theta and the original solution here, the temperature and essentially the heat flux, are continuous at this sort of artificial mathematical boundary that we have. So we kind of have this artificial mathematical boundary. And so there we're making this assumption, you know, which is physically motivated. The temperature doesn't know about any artificial mathematical boundary. The temperature is just going to flow as it naturally does. And if this is just a metal plate, there shouldn't be any difference, you know, it should just flow continuously. So these are our assumptions for the circular disk. Now, you know, for example, as I said, the geometry is so important. So for example, if we had an annulus, so here the origin is not included. So in this case, we wouldn't need that the solution has to be bounded at the origin, at the pole, or when r equals 0 assumption, because it's just not included. And here also infinity isn't included. So we'll talk about infinity in a second, but here r is not allowed to go to infinity, you know. So it's really a lot of it. It's important to think about the geometry. For example, with the wedge, we wouldn't have that periodicity condition. Here, there's no issue of picking a point and going around 2 pi. There's no going around because it's just this little pie-shaped piece. For the wedge, we really have the 3 boundaries. I've got this boundary here, this boundary, and then this curved boundary. And we do have to worry about the origin. For the wedge, we do have to put this boundedness condition at the origin, but that's about it. We don't need any other kind of, the temperature is continuous at some particular boundary. There's no, it doesn't loop back around like the closed disk. So keep in context these assumptions, in context to the geometry of the domain. It's really important now to, keep in mind the domain, because that's kind of making a difference here. Okay, so then, I guess the only sort of legitimate physical boundary condition is the temperature on the outer edge of this circular disk. So we're given the temperature distribution on the outer edge. Remember, there is no initial condition. Time is not a variable in this Laplace u equal to 0. This is a steady state calculation. And so we do separation of variables. It looks slightly different. It's in terms of the variables r and theta. And what exactly are we doing? We're taking, we're replacing u tilde by f of theta times g of r. So here, in this equation here, this u tilde gets replaced with f times g. Then you multiply both sides by r squared. Then you divide both sides by f times g. Then you'll have two expressions where the variables should be separated. And so then you'll move one set of equations to the other side and then set them all equal to negative lambda. And so when we do that for the f equation, we get something very familiar. This is the same f equation we get when you do the heat equation on a ring, where we're assuming the temperature and heat flux where the ring meets at its ends is continuous. So for the f equation, we've done this problem many times before, just we didn't do it in theta, we did it in x. One squiggle is really no different from the other. And for the g equation, we get something different here. We get this form here. And so now, as I said, for the f equation, we know the solution. And remember, for the ring, for the heat equation on a ring, we get the full Fourier series. So here we have the full Fourier series where, even lambda equal to 0 is an eigenvalue. For the g equation, we make the assumption that g equals r raised to the p to be determined. Then we plug it in to the g equation and we're able to solve for p. And so we're able to get that here, the solution here, is a basis of of two dimensions. So here, any solution by superposition will be a linear combination of r to the n and r to the minus n. But now, is where we have to think about the geometry and the domain. And here we made this assumption that the solution has to be bounded at 0. So the end result is we end up rejecting r to the negative n as a solution because of this boundedness requirement. And so the solution here in this geometry for this g equation, when n is not equal to 0, is just g equals c1 times r to the n. As I've mentioned, if this was an annulus, we'd keep both terms. And I'll show you what the annulus solution looks like in 1 second. So here, if n equals 0, we can do some calculus and show you that the solution, the eigenfunction for n equal to 0 is c1 ln of r plus c2. Again, the fact that we're on a closed disk, the domain, the geometry of the domain comes into play. We need the function to be bounded at the pole when r equals 0. So this natural log term, is a no-go. Can't have this. So our solution now for the n equal to 0 case then just becomes this constant. And as before, if we're looking on an annulus, for example, we would not have to get rid of the natural log of r. It's bounded on an annulus because r doesn't go to infinity. So we can form the product solution. And so very careful, Here's the G equation solution. And here is the F equation solution, the cosine plus sine. And we just distributed, we multiplied G to F and distributed across both terms. And so, you know, the next step is really optional. So some books will then now rewrite it this way. So what have we done? All we've done is multiply top and bottom by capital R to the N. Keep in mind, capital R to the N is a constant. Just multiply top and bottom. And we're giving this term now, A sub N tilde. So here, A sub N tilde times R sub N, I'm just going to call A sub N. And then the other R sub N, the R sub N that we divided by, that's down here. And you don't have to do this at all, you know, I mean, it'll still work. Everything, math is math, you know, math, it'll still work if you use this form. And I'll show you in a second. I'll do it both ways. So just for having something nice to work with, this is a little easier to work with when we're trying to show convergence, this form. And so that's why that's a nicer version to work with when you're especially trying to talk about convergence. If you know, just in general, the other form is fine too. So last step here, I want to find the coefficients for, you know, either form. Like I said, I'll do this in both ways. So we use the boundary condition. We know that when R equals capital R, so we're on the boundary of the circular disk now, there's some prescribed initial temperature if you want to think of U as the temperature. I'm thinking of this as a steady state calculation for a heat equation. And so when you when you plug in the capital R right here, this term goes to 1 and we get a Fourier series. And so now we know all about Fourier series. We now know we can calculate the coefficients using orthogonality. So now I can find a formula for these, which are a standard formula. And so, you know, there's a formal solution. Let's let's use the other solution for 1 second. So let me make this go away for 1 second. Just forget about this. Let's use this form here, the original form. There's nothing wrong with it at all. So look what happens. We're going to replace this R right here with a capital R. So let me replace all the other R. So this R right here will get replaced with a capital R. I'll put in the exponent. So here I have a capital R. And so here you get a capital R to the N. Remember, capital R is a constant. Here I get a capital R to the N. And here, this whole thing is equal to F of theta. And, you know, I go, oh, well, we still have a Fourier series, you know. Here, we just think of this now as a new constant. Just A sub N times R to the N, that's just a new constant. You can call it another letter, you know. And so we can solve, you know, just by Fourier series, we know A sub N times R to the N, that'll be integral 1 over pi by the orthogonality, 1 over pi minus pi to pi F of theta cosine theta. And so then you can, you know, this capital R to the N, you divide to the other side here. And so in your solution, in your coefficient, in the denominator is a capital R to the N, naturally speaking, you know, just from doing the algebra. So here I'd have F of theta cosine theta, blah, blah, blah. But then you divide by this R to the N. And so built into the A tilde coefficient is a capital R in there. And Here, this is just kind of putting it in at the beginning because it's a constant anyway. So whether you divide after you do the integral by capital R, if you divide before you do the integral by capital R, doesn't matter, it's a constant. So yeah, it'll all work out if you just are consistent and stick with the math. So if you don't like this form, that's fine. You can still use the original form, and if you just follow the math, you'll get the same answer at the end. I'll let you think about it. So I now want to change topics slightly. So here we've developed the formal solution on a circular disk. There'll be subtle differences if you change the geometry. And I'll talk about the annulus, which is kind of a most general solution because it has all the terms. And by turning off certain terms, you can find solutions to other geometries. So here we should talk about convergence and also the uniqueness of the solution. And so before I get, so we need some results here before we can talk about that stuff. So, okay, I think it's raining. So if you hear something, that's rain. So first, what I wanted to do was motivate the maximum minimum principle, because if you just look at the result in the setting of PDEs, it's kind of confusing, if not counterintuitive. So I first want to do baby steps. Let's look at the Laplace's equation in 1D. So what does that mean? I'm on a closed interval a to b, and I'm assuming the second derivative of some function f is equal to 0. So here, maybe instead of Laplace u, I should have said Laplace f here. So in 1D, all that's saying is f double prime equals 0. And we took Calc 1, we can integrate. So f double prime equals 0, integrate twice, you get f of x is kx plus c, where k and c are some constants. So after my first integration, I get some constant of integration, I called it k. After integrate one more time, you get kx plus my second constant of integration, I called it here little c. So now, for the sake of the theorem I'm trying to motivate, consider the following 3 cases for the slope. So for the slope k, we know, this is a real number, so k can either be less than 0, equal to 0, or greater than 0. And so, from calculus, that implies if, we either have a decreasing function, a constant function, or an increasing function, okay? So here's one important result to notice. In all 3 cases, the maximum and or minimum of the function is occurring on the boundary. But you're saying, well, not in case 2, Sujit. When k equals 0, the maximum also occurs in the interior. That's true, but in case 2, when the maximum does occur on the interior, the function is a constant. So that's something to notice about when, when the maximum or minimum does occur on the interior, that's the case when the function is identically constant. So that's something to keep in mind. Otherwise, if the function is not constant, or if another way to say it, if the maximum minimum is not occurring on the interior, it's occurring on the endpoints, so that's the only place it's going to happen. So in this case, these are the only places we see the max and min at the endpoints, the boundary basically of our domain. Here, for this domain, think of A and B as being the boundary. It's a very simple boundary, obviously, but that's the boundary. So that's one thing to notice. So that's one thing, that when you have Laplace u equal to 0, then the maximum or minimum is going to occur on the boundaries. If it doesn't, if the maximum occurs in the interior, then the function is constant everywhere. That's one thing right here from this example we want to notice. Here's another thing to notice. If you pick some point x naught, so here I'm going to pick some point x naught, and pick an epsilon neighborhood around x naught that's still inside the domain AB. So here now I have this epsilon neighborhood around x naught, but that's still inside the original domain AB. okay? So here now, I'm going to do some math here. Look what happens if you average the y value at the endpoints. So here's my x naught. Here's you know, x naught minus epsilon, x naught plus epsilon. What I'm doing is I'm taking this y value, which would be f of x naught plus epsilon, and I'm taking this y value, which would be f of x naught minus epsilon. I'm taking those two y values and averaging them. I'm adding and dividing by 2. So when we do the math, look what happens. You know, I know the function, I know what the function looks like. The function is just kx plus c. So I plug in, and here, this minus epsilon and this plus epsilon cancel. Everything else doubles up. But we're dividing by 2. So you get back the average value is the point, this point in the middle is the average value. So to say it in words here, f of x naught is the average value of the boundary points of any, you know, interval that it's contained in, that it's the center of, where that interval is entirely in our original domain. So here I did the picture. There's x naught, and there's your x naught minus epsilon, x naught plus epsilon. And now we're looking at the y values at the left and right endpoints. And when you average it, it turns out to be the y value at x naught. And this is true for any x naught. So what does that mean? Pick any point x naught, take a little interval around it. The y value at x naught will be the average of the y values of these boundary points of that interval. So here is the official result now in terms of PDEs and, you know, the setting we're looking at this material in. So first of all, let me remind you here, we came up with this series solution of this form. And we rewrote it so you get this capital R in the bottom. Like I said, this will be a nicer form to work with when we're doing the convergence discussion. And just using Fourier series theory, we can show a sub 0 is the average of the initial data. We know that from a long time now from working with Fourier series. Also note that a sub 0 is the value of our solution when r equals 0. Okay, so here, when I make r equals 0, so when I make this r equals 0, all these terms cancel out, 0 out. This whole thing disappears when you make r equal to 0. So 2 things. The temperature at the center is the average temperature of the temperature around the edge. That's a thing we've learned. That's what that's saying. But that's just one thing. So there's another fact here. So we can extend this idea to any circle that U naught is centered around. So I'm saying, in fact, U tilde at the pole, the temperature at the pole, is the average value of any circle, I guess it's down here, of any circle that you pick. Okay. Why? So here, the argument is kind of subtle. Okay. So here's the point that I thought I would already make, that if you look at any circle in the domain centered at the pole, the average value there will be the same. It'll equal the temperature at the center. Okay, so here's the argument. Here's the argument. So pick any circle here. Can I get it to match? Yeah, wow. Okay, glad I'm recording this. Pick any circle. Now, pose a brand new Laplace U problem. So I want to call this domain here, where this new circle, let's call that new domain D tilde. Remember, our original domain D is this big disk, the big disk, okay? So now we're going to pose a new problems. So here, say Laplace, let Laplace u equals 0 on d tilde. And you say, well, what about boundary conditions? We'll let u of, so let's say the radius here is r1, or I'll say r tilde, the radius of the domain there. So let u r tilde comma theta just be the temperature that we know from this solution. So whatever the temperature of this function is at r tilde, you know, let that be the temperature on this boundary. So I've got a new, I'll call it f tilde, I guess, but I hope that doesn't confuse things. There's no reason for me to introduce f tilde. So here, when you make little r equal to capital R tilde, I'm just going to call whatever temperature that is f tilde. Okay. So yeah, now we have this new Laplace u problem. And in theory, we can solve it exactly the same way. We'll solve it and get some kind of series solution where the first term will be the average temperature of the temperature on the edge. And the first term will also be the temperature when little r equals 0. But for this new problem, when the center is the same as the old problem. So, you know, I don't know why I wrote it on this slide, because I laid out the whole argument right here. So here's the argument again, done in notation that most humans hopefully will be able to read, not my chicken scribble. So here, for example, pick some radius r tilde and make the circle. See, I can't do that anymore. Make the circle. Shoot. Make the circle. Right. I'm just gonna try. So here's our circle. And like I said, now pose a new PDE. Laplace u in that circle with the boundary condition here, when the radius equals r tilde, let the boundary temperature be g of theta, where g of theta is just the temperature on that circle according to our solution, because we've already solved this problem on the bigger disk. So whatever the temperature is on that circle, make that your boundary condition. When you solve this, you get a series solution. And here, look, if you make r 0, then that takes us to the center, but that's also, you know, we know the temperature there as a function of u tilde. So here we can solve for w tilde using our same theory, and you get the same kind of Fourier series stuff. And for the a sub 0 term, again, it's the average. It's also the temperature at the center of the disk, but we've calculated the temperature of the center of the disk by solving the bigger problem, the Laplace u on the bigger disk. Here, there's a big disk and a small disk. Right here, the larger disk has radius r. Then we have a smaller disk here, radius r tilde, which is this disk right here. Bam, it's pretty close, not bad. That was good. I can live with that. So you compare the temperatures. Well, they're equal, but the temperatures are the average temperatures on their boundaries. So here we're concluding that, you know, if you take any circle centered at the origin, calculate the average temperature around the boundary of the averages will all be the same, and all those averages will equal the temperature at the center. And you should kind of think of what's happening as we get closer and closer to the center. I'm not saying the temperature on each circle is the same, just that the average temperature on each circle is the same. So that's the other thing. I'm not saying g of theta and f of theta are the same. That's not what we're saying. What we're saying is when you average the temperatures, they are the same. And those average temperatures are also the temperature at the center. And it's not just the center. In fact, you can pick any point. I can pick any point in the circle, draw a circle around it that's contained in the bigger domain, and pose a Laplace u equal to, or whatever letter you want to use, Laplace u equal to 0 in this new smaller domain, where you let the boundary data just be the temperature that we've calculated for u tilde. Then you'll get a series solution, and then we can conclude that the temperature here at this center is the average temperature of the temperature along any circle around it on the edge. So this slide is very important in terms of an analysis technique where we've posed a new PDE sub-problem. Here, remember, we've already solved the PDE on the bigger outer disk here. And now what we're doing, is a kind of sneaky analysis, is to pose a new Laplace u equal to 0 on a smaller region inside. We know the temperature already, and so this is a very slick analysis technique. So here's the formal statement of these results with, very general proof. I don't want to get so technical at this stage. If you can appreciate the technique here of posing the Laplacian sub-problem within the domain and using that to get results, that would be great. So here's the official result. So the temperature at any point x sub 0 in our domain, our circular disk, is the average temperature along any circle that's, around that point that's inside the domain. So let me draw a picture. Here's our domain. We pick any point. We claim the temperature at that point. Now, if you take any circle, and let's put a circle of radius r tilde, any circle of radius r tilde where the, that's around the point centered at the circle, then the temperature at this point, x naught, will be this average temperature along the edge of this circle. And it's true for any circle that you pick that, that's around that point. So now if I pick another circle with x naught at the center, it'll be the same thing. You can pick any circle with x naught at the center. Of course, it's also true at the very center of the disk, but it's true at any point. At the center of the disk, we additionally know the temperature actually is the average of this edge temperature of the entire disk and any circle, that's around it. So as I mentioned, the proof is to pose a new Laplace U problem within the disk. So here, Laplace U will equal 0. If it's 0 on the domain D, then it'll be 0 on any circle centered in that domain D, because the Laplace U equal to 0 everywhere in that domain D. So we can pose this subproblem, pick the circle around x naught, and create a new Laplace U equal to 0 problem with that as your new domain. And in that subproblem, you can find the series solution where it turns out the series solution tells us the temperature at the center of the circle is also the average temperature of the temperature on the edge of that circle. And so that's where we, get this result. And so a direct result of this, so it's called the mean value theorem, this idea that any point is the average temperature of the temperature along any circle, that's centered at that point, that's inside the domain. That's known as the mean value theorem for Laplace. And you saw why it's this averaging that's happening. So here, in 1D, remember what's happening here. You pick any point x naught. I can show you x naught is the average, the y value at x naught is the average of the y value on the endpoints. That's what we've got going on here. So here's a direct result now is the maximum minimum principle. So maybe let me do the argument first. So here's our circular domain. I'm interested in finding where the maximum temperature is occurring. So pick a point. Is it possible the maximum temperature occurs there? Is it possible that the highest or lowest temperature is occurring at this point? Well, let's think about it. You know, based on our analysis, if I pick a circle, if I take any circle centered around that point, we know the temperature at the center of that circle is the average temperature. Think about the word average. If it's an average, it can't be the largest or the smallest, unless it's a constant. Because when you take an average, the average value is always in between, right? An average value isn't the largest or the smallest unless you're dealing with a constant function. So by contradiction, it's not possible for a maximum or minimum value to occur inside the domain unless you're dealing with a constant function. So just assume it's not constant. Pick any point and ask the question, can the max or min occur here? And the way we answer the question is we say, well, if you draw a circle around that point, we know the temperature at the point will be the average temperature of the temperature on the circle. And if it's an average, it can't be the largest or smallest, you know, unless it's a constant. Here we're assuming it's not constant. So it's not possible for the max or min to occur on the interior. So the max or min would have to occur on the boundary in the case that the function is assumed to be not constant. So here we go. Let's read it again slowly. In steady state, assuming no sources, the temperature cannot attain its maximum in the interior, maximum or minimum, in the interior, unless the temperature is constant everywhere. If the temperature is not constant, then what happens is, since the max or min cannot occur in the interior, then it has to occur on the boundary. And once again, I refer you to our thought experiment where we have both things happening. You see your max and mins occurring on the boundary. And here you can show any point is the average value of the values on the boundary of any circle that it's the center of. Here, a circle just looks like this interval. This is, if you take a circle and make it one-dimensional, you just get this part here. It's just this part. So this is a very powerful result that we get. That it's not obvious if you solve this problem on a non-circular domain. It's not obvious, and so specifically looking at this problem on a circular domain, we got this super nice result. And the maximum principle and minimum principle is what it's called, allows us to also prove uniqueness. So so a whole lot of deep stuff just happened, y'all. And so I want you to take it slow. There's two things. One is the idea of posing the sub-problem. So think on that for a hot minute. And then from the sub-problem, we get this result that the temperature at any point is the average temperature, of the temperature of a circle, the temperature on a circle around it. So those are two kind of tricky things, and from those two things we get these two results. Okay, so think about it multiple times. Evan.
So does this imply that anywhere in the interior where the gradient is 0 has to be a saddle point?
I guess so. The gradient's different from the Laplace though, right?
Sure, but if we're trying to find...
Laplace is del dot del u though, right? So if the gradient is 0, then the Laplace will be 0, right?
So I mean, it's a saddle point then, right?
I think so. We get a saddle point, so you have to check. There's still one more condition to check for saddle point, I think, because we check if We check the determinant of something. There's
The
this
Hessian, I think.
Yeah, right, the Hessian. So I don't know if we still need to check the Hessian.
But just geometrically, if it can't be a maximum or a minimum.
Oh, but yeah, the geometric, you're right. I was forgetting about the maximum principle. I just went straight math. Yeah, I guess so. That would, I mean, I guess that's why this is some type of weird equilibrium. Some kind of weird balance point. Yeah, like a weird saddle point. Great comment, Evan. So let me talk about convergence, since we have a series. The convergence is actually really easy. So we claim that if you have Laplace u equal to 0 in an open region, then u is smooth. It's infinitely differentiable, and their derivatives are continuous. So as you know, here's our formal solution written in this alternate form where we have the divided by the capital R to the n. So here, one thing we know is if f of theta is piecewise smooth, then we can bound those coefficients. If it's piecewise smooth, we're not letting the function or its derivatives blow up anywhere. We're not allowing infinite discontinuities, only jump or removable discontinuities. It's, so it's on a finite domain. So the coefficients are well behaved, no problem. Now, we know from Fourier series theory, if this thing converges, when R equals capital R, it'll converge. It always, you can always think about it, always converges to the average, right? So in general, if R equals capital R, it'll converge to the average. If R equal to 0, it equals a sub 0. Remember, if R equal to 0, these terms zero out, and you're just left with a sub 0. And for R in between, I'll show you now, the series will be absolutely convergent. And so here we'll need a little analysis. Remember, for this result, we're just using, this result comes from our Fourier series theory. We know when R equals capital R, this thing, the series becomes a Fourier series. And we know for Fourier series, as long as our data is piecewise smooth, then we'll have that convergence to the adjusted periodic extension of the function. So that's what all that mumbo jumbo is there. At R equal to 0, you can just algebraically see you don't have an infinite series, you just have a single term. So the question is, okay, when R is in between, and our, we don't have Fourier series theory that we can use here. So here we're going to just do some good old-fashioned sequences in series, and I'll show you we actually have a geoseries. So if R is in between 0 and capital R, in particular, little r over capital R is between 0 and 1. And if I now raise that to the nth power, that becomes a decaying term. So this right here is an exponentially decaying term, because little r is, this expression is between 0 and 1, and we're raising it to the nth power. So that bodes well for convergence. So by triangle inequality, I can bound the series. So I'm looking at the series without its first term. I know the first term is finite already. So I'm gonna add there's no a sub 0 term here. I'll add that in at the end. Okay, so just watch out here. So, okay, so here by triangle inequality, we can look at the, series of the absolute values of the terms and bound the terms. So here, the cosine and sine terms, we can bound by 1. That's not an issue. The a sub n and b sub n terms, if we assume f is piecewise smooth, they're bounded by some constant. So all we're left with is the little r over capital R term raised to the n. But now, because little r over capital R is a number between 0 and 1, we can think of this essentially as a geoseries. And here they're the same, so I added them. And now, using geoseries result, you can find the sum. Here, for the full geoseries, I'd need a n minus 1 here. So that's why this extra r over capital R to the n term is appearing in the numerator. And so, yeah, the right-hand side here is a finite number. So now let me add in the other term. So we add in the a sub 0 term, which I know is also bounded because f is piecewise smooth. And so, yeah, we've shown the original series solution is absolutely convergent. Because what we've shown is if you take the absolute value of all the terms, we've shown that's going to be less than this, which is a finite number. So we have absolute convergence for each r inside the interval, and absolute convergence gives us uniform convergence. And if you take the derivative, derivative with respect to theta, you get this n term, but we always have this exponentially decaying term. This term is an exponentially decaying term. So it's always going to go to 0 faster than any polynomial. And in fact, we can just write it as an exponent, right? We can write it as e to the n ln of r over r. And here, be careful. Here, this is a negative number because r is less than capital R. R over capital R is between 0 and 1. Ln of r over capital R is actually a negative number. This is a decaying exponential term. So to be very explicit, I wrote it this way. I put absolute values here and then threw in the minus symbol so you can see it explicitly. So yeah, this term here is always a decaying exponential term that's gonna go to 0. And for example, for this first derivative, you can bound it. Yeah, we have this n term up here, but then you can now use a ratio test to show that this series converges. And that's true if you take derivatives with respect to r as well. You just get an n coming down, 1 over capital R, but it's still being multiplied to an exponentially decaying term. So it's just the exponentially decaying term is too strong. So yeah, we have very nice smoothness for Laplace u equal to 0 on this domain. Let me wrap up here. I guess I'm done here. Let me just talk about the annulus. For the annulus, we have the ln of r part as well. You remember the original solution, we had a constant plus this natural log term, but if we included the origin, then we couldn't have the natural log term. But in the annulus, we don't include the origin, so we can have the natural log term. And then here's the r to the n term. So this looks like the regular solution. But we also had an r to the negative n term. And here I use a different index just to kind of keep the two separate, but you could still use n. Here, this is, so if you remember when we solved this, the G equation for the n not equal to 0 case, we got r to the n and r to the negative n as basis elements. And then, we said, since we've included the origin for the circular disk, since we included the origin, we had to get rid of this. But now we're not including the origin and we don't have to get rid of this term. And so here you can see this r to the minus n term is represented right here in a second series. I put it down in the denominator. And here, we've divided by particular constants just to make it look nice. Again, you don't need this part. So these are the inside and outside radius of the annulus. And so this would be the most general solution. It's like I said, if you include the center, then we'd get rid of, so suppose we include the pole, then we'd have to get rid of this part and this part. You can kind of, by thinking about what's included and what's excluded, you can find solutions to other geometries. If we were outside of the disk, then we would have to get rid of this part. If you're outside of the disk, r going to infinity, we can't have that. And you can't have this part if you're outside of the disk. So the solution of outside of the disk would be the solution for if you're outside of the disk. So you can find other solutions from this sort of most general solution that has all the terms. So Yeah, I'm basically done. I'll need to talk about uniqueness, which is very straightforward and very easy. We get it from the maximum principle. And so I'll finish up that next time. And then the next couple of slides are just summarizing our discussion of all the PDEs. And then we'll move on to Fourier transforms. And then we'll talk about dispersive waves. And then the more student-led portion of the class with the projects will begin. All right, everybody, so I'm going to stop right here.